I'm going to visit with you a little bit about a particular project in shelter belts relative to hydrogen sulfide emissions from swine barns. There was some work done in Australia, and their modeling said just beyond the shelter belt, we're going to get about 50% reduction in odor. But as we move away in distance, at some point there will be no effect. How much credit can we give to the shelter belt? Should we give the 50%, or as we move away, should we give less and less? And that was the premise for my research. We took a site that was way out in the middle of nowhere on a relatively level site where we don't have topography involved. We wanted to measure the effect the shelter belt has on hydrogen sulfide dispersion. We chose hydrogen sulfide over odor, being that there is really not a good instrument to measure odor other than the human nose, whereas we can have electronic instruments to measure hydrogen sulfide. What is the effect of shelter belt porosity? In other words, is there 1 row, 2 row, or 3 rows be more effective, and how much more effective? Secondly, we know that the atmosphere has various stability classes, and I'm going to talk about that in a little bit later. So we took this basically uninhibited site, and we said we're going to put in a windbreak along this area right here, and we're going to spade in our trees. So we can measure the same source, which is the barns right here, with and without a shelter belt. We used an SPM monitor that we were accurate within 2 parts per billion. We put our monitors out at the beginning before the building site so we could get the background, and then we put them just right outside the building, as well as just beyond the trees, and then at distances up to a half mile away. We knew in the summertime that the winds are out of the south, southeast. To the right of your screen is to the north, the up is to the west, and so the south is off to the left. This is a picture of the site without the shelter belt. In the bean field next to the building site, we set up our monitors. They consisted of a pole and the hydrogen sulfide monitor here. We measured at 2 different levels, right above the beans at 1 meter above the ground, and as well as at 5.5 meters above the ground. We used a weather station to monitor the direction and the airspeed and the solar radiation to obtain our stability of our atmosphere. The next slide shows the first row of trees that were spaded in. We measured each of these situations for about 6 weeks. When the wind was blowing out of the south or southeast, we kept that data. When the wind happened to be blowing out of any other direction, that data was discarded. And then after we finished that, we spaded in a second row of evergreen trees, and they provided a little more restriction. Each of these 2 rows were approximately 15 to 20 feet tall. The third row of trees was a little bit taller. It was about 25 to 30 foot, and it was on the back side of the shelter belt. I wanted to show you the porosity differences between each of the rows. The first row had approximately 84% porous. It was quite open. The second row was about 51% or 50%. We were only 38, 40% on the third row. So we could analyze the data from different porosities and begin to work on a model that would kind of predict what each of the trees would do. The stability of the air is defined into 6 different classes according to the U.S. Weather Service, and they use A, B, C, D, and F, which go from very unstable air to stable air. The stability is based on the cloud cover, the amount of solar radiation that we have, the wind speed, the air temperature. Very unstable air would be a bright sunny day, and that we have a very definite temperature gradient from the soil on up to higher elevations. We have quite a bit of vertical movement. So even if we don't have any wind, we can have a very unstable situation and get a lot of mixing of the air. Whereas in a stable situation, such as classes E and F, they would be described as a cloudy day towards the evening, a very low wind, maybe 1 to 4 miles an hour, something that's going to keep that plume together, and we're not getting any dispersion. During the experiment, we experienced this many frequencies of occurrences of the various stability classes. Not very much unstable air. Most of the time we were in a neutral situation, a C or D, and very little time that we had a very stable air. And so based on that, we were able to analyze the data in various situations. So this would be at both the 5.5 meters as well as the 1 meter height without any shelter belt. We see that right above the beans that we had very little difference in hydrogen sulfide concentration as it moved away from the building downstream. This particular red line is about 7 parts per billion. Between 5 and 7 parts per billion is the detection odor threshold. In other words, we need at least that much hydrogen sulfide in the air before an average person can detect it. But if we look up at 5.5 meters, we can see the general shape of the curve when it's very stable air that was similar to what was measured by that earlier research that we talked about. As we get into unstable air, we see very little change as we move downstream. So even without a shelter belt, unstable air is very effective in reducing the hydrogen sulfide coming from the particular building. If we look at with one row of trees, we see now that 1 meter height is very similar to without any shelter belt. Whereas in the elevation at 5.5 meters, we have a decrease in the initial amount of hydrogen sulfide just beyond the trees. It was above 20 parts per billion before, and now it's about 13 parts per billion. But as we moved away from that, we have very little difference in effect. And if we go all the way out to 3 rows of trees where we had the most of the porosity decrease, we see that even at 5.5 meters, there's very little difference between that and 1 meter. So if we look at very stable condition, the E and F situation, and compare with and without shelter belts. So the blue line on 5.5 meters without any shelter belts. Here is 1 row of trees, and here are 3 rows of trees. And so as we move away from the shelter belt, we find that there is very little difference beyond 500 meters with or without trees. At the 1 meter height, there's very little effect, and there's no significant difference between any of these values with our accuracy of our instrument. So what does that mean? Our conclusions were that the effect on hydrogen sulfide of a shelter belt is most of the reduction occurred just beyond the shelter belt. Approximately after 500 meters, there's very little effect whether the shelter belt was there or not. Atmospheric stability certainly did have an effect on the dispersion. So what is our recommendation? For one thing, we would probably recommend for the maximum effectiveness of a shelter belt, you really want the recipient to be just beyond the shelter belt. In other words, should we plant these shelter belts for the benefit of odor or hydrogen sulfide near the recipient? The other recommendation might be on the same site where the producer lives, that he place a shelter belt between the odor source as well as where he lives. Now, these recommendations are only based strictly on the effectiveness of reducing hydrogen sulfide. That's not to say that there are not other very good reasons for planting that shelter belt around the building site or the source. You would probably put the shelter belt around the source for aesthetics, or you might want to put it around there for dust removal, just because we might not have the biggest bang for our buck in reducing the odor. There are many other good reasons for putting that shelter belt out.